Welcome, everyone. I'm excited to kick off today's presentation on Chapter 4, which is all about streams and file I/O. This is part of our advanced programming series. We'll explore how to handle data streams and perform input and output operations with files. Over the next few slides, we'll cover key concepts, techniques, and best practices that will help you manage data efficiently in your programs. Let's get started. Let's take a closer look at our objectives for today. First, we'll delve into the concept of files and streams, understanding what they are and how they function within programming. Then, we'll compare text files and binary files, highlighting their key differences and when to use each. Finally, we'll explore the practical aspects of working with files, including how to create, write to, and read from them. These skills are fundamental because they enable us to handle data efficiently and effectively in our applications. By the end of this slide, you'll see how these concepts connect and support the broader theme of managing data in programming. Let's talk about how programs need to communicate with the outside world. This is a fundamental part of how software interacts with users and other systems. The main ways they do this are through input and output. For example, input could be something like a keyboard, where a user types commands or data. Output, on the other hand, might be the computer screen displaying information or results. But communication isn't limited to just immediate input and output. Programs can also share information indirectly through stored data, like files. These files serve as a way to save data for later use or to exchange information between different programs or systems. Understanding these communication methods is key because it helps us see how programs function within a larger environment, not just in isolation. It also sets the stage for discussing how programs handle data and interact effectively with the outside world. Let's take a closer look at I/O, which stands for input and output. In this context, it refers to the data going into and coming out of programs. When we talk about input, it can come from various sources like a keyboard or a file. Output, on the other hand, can be directed to a display screen or saved into a file. Now, why do we emphasize file I/O? One key advantage is that it creates a permanent copy of the data, which can be useful for record keeping or future reference. Additionally, output from one program can easily become input for another, enabling seamless data processing workflows. Another benefit is that input can be automated, so instead of manually typing data each time, programs can handle data automatically, saving time and reducing errors. It's important to understand that the data source or destination isn't limited to just files. It can be anything capable of holding, generating, or consuming data, like a peripheral device, a network socket, or even an array within a program. This flexibility is fundamental to how programs interact with their environment and process data efficiently. Data stored in variables and arrays is temporary, meaning it only exists while the program is running. Once the program terminates, that data is gone. But for long-term storage, computers rely on files. You probably use files every day, whether you're writing a document or creating a spreadsheet. Files are essential for saving information beyond the immediate session. These files are stored on secondary storage devices like hard disks, optical disks, flash drives, and magnetic tapes, things we use regularly to keep our data safe. The key point here is that data maintained in files is known as persistent data. Unlike variables that disappear when a program ends, persistent data exists beyond the life of the program that created it. This allows us to access and use our information whenever we need it, across multiple sessions. Let's talk about how Java views files. Essentially, Java treats each file as a sequential stream of bytes. This means that when you're working with files, you're handling a continuous flow of data, one byte after another. Now, every operating system has a way to tell us when we've reached the end of a file. This could be through an end-of-file marker or by providing a count of how many bytes are in the file. When a Java program processes this stream of bytes, it simply receives a signal from the operating system indicating that it has reached the end. The great thing about this approach is that the program doesn't need to know the specifics of how the underlying platform represents files or streams. It just reacts to the signals it receives, making Java's file handling both flexible and platform independent. This abstraction is a key part of how Java allows us to write code that works seamlessly across different systems. Let's talk about the different types of streams we use in file handling. File streams can be used to input or output data, and they handle this data either as bytes or as characters. When we use byte-based streams, we're working directly with the binary format of the data. For example, if we store the number 5 in a byte stream, it would be saved as its binary representation, which is 101. On the other hand, character-based streams handle data as a sequence of characters, or Unicode. So if we store the number 5 using a character stream, it's stored as the character 5. In binary, this character 5 is represented as 0110101, which is the Unicode or ASCII code for the character. Understanding the difference between these two is key because it affects how data is stored and retrieved, especially when dealing with text versus binary data. This distinction is fundamental as we explore more about data input and output in programming. Let's take a look at the difference between these two forms. When we talk about numeric values, like the number 5, they can be used as integers in calculations. That means we can perform arithmetic operations with them. On the other hand, the character 5 is just a symbol, a character within a string of text. It doesn't have any numerical value or ability to be used in calculations. Now, moving on to file types. Files created using byte-based streams are called binary files. These contain data in a format that isn't directly readable as text. Conversely, files made with character-based streams are referred to as text files. These are easier to read and edit because they contain human-readable characters. Speaking of readability, text files can be opened and read easily using text editors, like Notepad or TextEdit. Binary files, however, require specific programs that understand the structure and content of the file to interpret the data correctly. These programs can convert the binary data into a human-readable format, but they can't be simply opened with a text editor. Understanding these differences is essential because it affects how we handle, process, and interpret different types of files in our projects, tying back to the overall theme of effective data management. Now, let's talk about the difference between binary and text files. All data and programs at their core are just zeros and ones. But how those zeros and ones are interpreted makes all the difference. When we're dealing with text files, the bits are used to represent printable characters, things we can read easily. For example, Java source files are text files, and so are any files created with a simple text editor. That makes text files much more human-readable, which is a big advantage when you're trying to understand or edit data directly. On the other hand, binary files use the bits to encode other types of information, such as executable instructions or numeric data. These files are designed for the computer to read efficiently, but they're not really meant for humans to interpret directly. Now, specifically for Java, you'll see that Java source files are text files. They're the code we write, and they're readable. Sometimes, these source files are used as input or output files in a program. Conversely, Java also creates binary files, which are the compiled executable files. These are typically the files the computer runs, and they're usually for input or output purposes once the program is in use. So, the key takeaway here is that text files tend to be more human-friendly, while binary files are optimized for machine processing. Both play vital roles in how we develop and run software, fitting into the larger picture of data handling and program execution. Now, let's discuss how Java handles input, output, and error streams. When a Java program opens a file, it does so by creating an object that associates a stream of bytes or characters with that file. This process involves the object's constructor communicating with the operating system to actually open the file. But Java's capabilities go beyond just files. It can also connect streams to various devices. For example, when a program starts running, it automatically creates 3 key stream objects linked to devices. These are systemin, systemout, and systemer. Systemin, which is the standard input stream, typically allows a program to receive input from the keyboard. This setup is fundamental because it enables user interaction with the program. Understanding these streams is essential because they form the backbone of how Java programs interact with their environment, whether reading data, displaying output, or handling errors. This connection between Java and the operating system's devices is a core part of how Java manages input, output, and error handling across different platforms. Let's take a closer look at the object system out, which is the standard output stream object. This is what we typically use to display character data on the screen. Think of it as your program's way of printing messages or results for the user to see. Similarly, we have systemer, which is the standard error stream object. Its primary role is to output error messages, also to the screen, but specifically for errors or warnings. This separation helps us distinguish between normal output and error messages, making debugging easier. Now, an important point is that each of these streams, system in, system out, and systemer, can be redirected. This means we can change where the input or output comes from or goes to. For example, instead of reading input from the keyboard, we could read from a file, and instead of printing to the screen, we could send output to a file or another device. Specifically, for systemin, redirecting allows the program to read bytes from a different source, like a file or network stream. For system out and systemer, redirecting can send output or error messages elsewhere, such as to a file, a printer, or even over a network. And how do we do this? The class system provides methods like setin, setout, and setter. These methods allow us to redirect the standard input, output, and error streams dynamically at runtime. This flexibility is powerful because it enables us to control how and where our program interacts with the outside world, which ties into our overall theme of making our programs more adaptable and versatile. Now, let's talk about how programs handle reading and writing information. When a program needs to get data from a source, it uses what's called an input stream. Think of it as a channel through which data flows into the program, and it reads one item at a time. This approach helps the program process data efficiently, especially when dealing with large amounts of information. On the flip side, when a program needs to send data somewhere, like saving results or sending output, it uses an output stream. Just like with input, data is written one item at a time to the destination. This method ensures that data is transferred accurately and in a controlled manner. Both of these concepts, reading and writing through streams, are fundamental to how programs interact with external data sources and destinations. They help us manage data flow smoothly, which is essential for building reliable and efficient software systems. Now, let's take a closer look at the Java I/O package, which is essential for file processing in Java. This package provides the classes we use to read from and write to files efficiently. For example, when working with byte-based data, we use classes like FileInputStream and FileOutputStream. These are great for handling raw byte data, especially for binary files. On the other hand, if we're dealing with character data, we turn to FileReader and FileWriter, which make it easier to work with text files by handling character encoding behind the scenes. These classes are actually built on top of more general abstract classes like InputStream, OutputStream, Reader, and Writer. That means they inherit core functionality, but are specialized for specific types of data. Looking at the example on the slide, we see a line of code that combines FileWriter and FileOutputStream to create a writer for a file called smiley.txt. This setup allows us to write character data directly to a file through the output stream, making file handling more flexible and efficient. Overall, understanding these classes and their inheritance hierarchy helps us manage file input and output smoothly, which ties into our broader goal of mastering file processing in Java. So, in addition to the Java I/O classes we've discussed earlier, there are these two important classes for character-based input and output, scanner and formatter. The scanner class is really commonly used, especially for reading data from the keyboard, making it easy to get user input. But it's versatile enough to also read data from files, which is pretty handy when working with larger data sets. On the other hand, the formatter class is all about output. It allows us to produce formatted data, similar to how system out print works. This means we can control the appearance of our output, making it more readable and professional. To give you a quick idea, let me show you a simple example. Imagine creating a scanner object to read user input and a formatter object to output formatted results. These classes make input and output operations much more straightforward and flexible, especially when dealing with text-based data streams. Overall, these classes really extend our ability to handle character data smoothly, fitting well into our broader goal of effective I/O management in Java. Let's talk about the class file. It's really useful when you want to get information about files or directories on your disk. Now, it's important to note that objects of the file class don't actually open files or do any processing with the file contents. Instead, their main role is to represent files or directories so you can work with them in your program. You'll often see file objects used together with other Java I/O classes, especially when you need to specify which files or directories you're going to manipulate. When creating file objects, there are 4 constructors available. The most common one takes a string as an argument, which is the name of the file or directory you want to work with. What's really handy about this is that the string can include path information, not just the name itself. This way, you can specify exactly where the file is located on your system, making your code more flexible and precise. So, in summary, the file class helps you identify and work with files or directories, and understanding how to create these objects properly is key to managing file operations effectively in Java. Let's talk about file and directory paths. First, an absolute path. This is like giving someone the full address to a location, starting from the root directory. For example, see /home/index, HTML. It shows the complete root from the very top level down to the specific file or folder. Next, we have relative paths. These are more flexible because they start from the current directory where the application is running. Think of it as giving directions relative to your current location. For instance, index, HTML or home/index, HTML. These paths are useful when your location is already known or within a certain folder structure. Now, when creating file objects in Java, the constructor can take 2 string arguments. The first can be either an absolute or a relative path, and the second is the specific file or directory you're working with. This helps you specify exactly what file or folder you're referring to based on the path provided. There's also a constructor that uses an existing file object to specify the parent directory, combined with a string for the target file or folder. This approach is handy when you already have a file object representing a parent directory and want to build upon it. Finally, there's a constructor that accepts a URI object. Remember, a URI, or Uniform Resource Identifier, is a more general way of locating resources, including files. It's similar to URLs used for websites, but applies to local files too. This method gives you flexibility in locating files across different environments or protocols. Understanding these different path types and constructors is key to managing file access effectively in your applications, especially as we build more complex systems that interact with various resources. Let's talk about sequential access text files. First off, Java doesn't impose any specific structure on a file, which means you have the flexibility to organize your files in a way that best suits your application's needs. When you're retrieving data sequentially, the typical approach is to start at the beginning of the file and read through all the data until you find what you're looking for. It's like reading a book from start to finish until you reach the desired chapter or page. One important point to keep in mind is that editing data in many sequential files isn't straightforward. Because of how the data is stored, modifying a specific piece without risking damage to other data usually isn't feasible. Instead, the common practice is to update a record by rewriting the entire file. This may seem inefficient, but it's a practical approach given the limitations of sequential access. Overall, understanding how sequential files work helps you appreciate their role in data storage and retrieval, especially when designing applications that need to process large amounts of data efficiently. Quando queremos pegar dados de arquivo de forma sequential, começamos do inicio e lemos tudo, até encontrar informação que precisamos. E acute como falar livro até achar o capítulo desejado. Às vezes, durante a execução do programa, pode ser necessário passar várias vezes pelo arquivo, sempre do começo, até localizar o dado querido. E aqui entra ponto importante. A class scanner, que muitas vezes usamos para ler arquivos, não permite que a gente volte para o inicio do arquivo depois de começar a leitura. Então, se precisar reler o arquivo, o que devemos fazer é acute fechar o arquivo de lado e abrir ele novamente. Isso tudo reforça a ideia de que, ao trabalhar com leitura sequential, é acute fundamental entender essas limitações e estratégias, para garantir que nossos programas funcionam de forma efficient e confiável. Now, let's talk about object serialization in Java. Essentially, Java provides a mechanism that allows us to write entire objects to a file, which is incredibly useful for saving and retrieving complex data structures. When we serialize an object, it gets transformed into a sequence of bytes. These bytes aren't just random. They include the actual data stored in the object, as well as information about the object's type and the types of data it contains. Once an object has been serialized and written into a file, we can later read that file and deserialize the bytes to recreate the original object in memory. This process is vital for tasks like saving application state or transmitting objects over a network. To handle this process, Java offers classes like ObjectInputStream and ObjectOutputStream. These classes make it straightforward to read objects from a stream or write objects to a stream, simplifying the serialization and deserialization process. However, it's important to remember that only classes that implement the serializable interface can be serialized and deserialized. This acts as a safeguard, ensuring that only objects explicitly marked as serializable are processed this way. Overall, object serialization is a powerful feature that, when used correctly, can significantly enhance how we manage data persistence and communication in Java applications. All right, let's walk through this example together. Here, we're creating and writing to a file using the file and printwriter classes in Java. First, we declare a file object called file and set it to refer to txt. This is the file we'll be writing to. Then inside the try block, we create a printwriter object named output, passing the file as an argument. This is how we open the file for writing. Once the printwriter is set up, we can write lines of text to it using the println method. In this case, we're writing G3comp and A, B, and C to our file. It's important to remember that after we're done writing, we need to close the printwriter, which also closes the underlying file stream. This ensures all data is properly saved and resources are released. And of course, we handle potential I/O exceptions with a catch block, which helps us manage errors gracefully. So the key takeaway here is that creating a file and writing to it involves initializing a file object, using printwriter to write data, and always closing the stream afterward. This example nicely demonstrates how to perform basic file output in Java, which is fundamental for many applications that involve data storage or logging. Let's take a closer look at this example, where we read data from a file using the scanner class. First, notice that we create a file object pointing to txt. This is the file we want to read from, and it's important to ensure that this file exists in the correct directory. Then, inside the try block, we initialize a scanner object called read, passing the file object to it. This allows us to read the contents of the file easily. Next, we use readNextLine, twice to read the first and second lines from the file, storing them in variables name1 and name2. It's crucial to close the scanner after we're done, which helps prevent resource leaks. Finally, we print out the contents we read from the file. If an I/O exception occurs at any point, say, if the file isn't found or there's an access issue, the catch block handles it gracefully by printing an error message. This example highlights how the scanner class can be effectively used for file input, which ties into our overall theme of file handling in Java. It demonstrates the importance of proper resource management and error handling when working with files. In this example, we're demonstrating how to write to a file using the FileWriter class. First, we create a file object named myfile, which points to a file called test1.txt. Then, inside the try block, we instantiate a FileWriter object called fwrite, passing in our file object. This sets up the connection to write data into that file. Next, we use the write method to insert the string "Hi Java learners" into the file. After writing, it's important to flush the stream to ensure all data is properly written out, and then we close the FileWriter to free up resources. If any I/O exceptions occur during this process, they are caught in the catch block, and an error message is printed. Overall, this example highlights the key steps: creating a file object, initializing FileWriter, writing data, flushing, closing, and handling exceptions. It ties into our broader theme of file processing, showing a simple yet essential way to output data to files in Java. Notice that in Java, there are different classes specifically designed for read and write operations. It's important to understand that these classes serve different purposes and are used in different scenarios. For example, classes like file, FileWriter, and FileReader are commonly used when working with files. When practicing, I encourage you to create files, then try writing data to them, and finally read that data back. This hands-on approach helps solidify your understanding of how these classes work together. Remember, mastering these file operations is a key part of becoming proficient in Java I/O. It connects to the overall theme of learning how to handle data effectively within your programs. So, take the time to experiment with these classes. It's a crucial step toward writing more robust and data-driven applications. All right, let's wrap things up with this quick quiz to test our understanding of the advantages of file I/O now. When we talk about text files versus binary files, there are some key differences to keep in mind. Text files store data in a human-readable format, which makes them easy to edit and view with basic tools. Binary files, on the other hand, store data in a format that's directly usable by programs, which can be more efficient but less accessible to humans. Understanding how to create, write to, and read from files is essential. Creating a file involves opening it in the appropriate mode. Writing data means sending information to the file, and reading involves retrieving that data for use. These operations are fundamental to managing data effectively in programming, and mastering them really unlocks a lot of potential in how we handle information. So, keep these concepts in mind as they tie back to our overall goal: making data management seamless and efficient in our applications.